So in the previous lecture, we went over kind of the basics of creating an Euler diagram, right? Of using that to kind of model an argument. And we looked specifically at an example showing that universal instantiation, or the modus ponens form, was valid. And I've got a couple more examples for us to look at to get a little more practice with this. And in the second example here, we're going to look at a bigger one so you can see how this works with a larger argument. So what I have here, again, is a specific example of the modus tollens argument. And looking at the first statement here, all squares are rectangles, right? So in other words, if I rewrite this, right, using in the conditional language, if S is a square, then it's a rectangle. And then you notice, so down here we have not a rectangle, so that would be not Q, and the conclusion is not a square, which would be not P. So this is following that modus tollens format. All right, so how can we diagram this, right, and confirm what I kind of just told you before, that this is a valid form. So let's see. First, I need two circles. I need one for squares and one for rectangles. Right, so I'll do a circle to represent all squares, and because all squares are rectangles, that has to go inside the rectangles circle. All right, so now my second statement here, we're looking at a specific shape that is not a rectangle. So remember, individual items, individual objects get represented by dots, not circles. So I need to put a dot on my diagram for S, and because S is not a rectangle, it has to go outside the rectangle circle. So my question is, does this mean that S is also not a square? Well, yes. S is not in the square circle, and in fact, there's no way it could be. There's no possible way I could slip S into that square circle. So my conclusion here is that this is therefore a valid argument. Okay, so I've got a bigger one here, right? I've got a bigger one. We've got more than one circle here to think about. All right, so let's kind of start walking through this and see how we can diagram this. So first, we have to have a circle for tall people and another one for wealthy people. And the tall people, all of them are wealthy, so they need to be inside the wealthy circle. All right, now let's look at the next one. All wealthy people are admired. Okay, so wealthy people need to be inside the admired people circle. All right, now how are we going to do this next part? Some basketball players are not admired. Okay, so we talked previously about how to do how to do an existential statement, right? I know that my basketball player circle needs to overlap but not be contained in the admired circle. Right, well, work with me for I'm just going to make my tall people circle a little bigger. It's going to make this next part easier. Now I'm just making a hot mess. There we go. Okay. So how am I going to draw this? Well, I need to draw this in the most generic way possible. So what I don't want to do is this. Right? Yes, that does illustrate some basketball players are not admired, because there are some outside the admired circle. But I need to do this more generally. I'm going to draw this like this so that it overlaps all three of the circles, because that's possible. There's nothing in the statement that would lead me to believe that I should not put some of these basketball players into the tall and wealthy categories, right? So I'm going to try to kind of make this as inclusive as possible. So let me now label this basketball players. Now I've got all three of my first group of statements here, all three premises. So what's the conclusion? Some basketball players are not tall. Okay, well, looking at my diagram, are there basketball players who are not in the tall circle? Well, yeah, anyone out here is not tall. Anyone out here is not tall, or in here, yeah, absolutely. Our argument does allow the possibility, our diagram allows the possibility that some basketball players are not in that tall category. So this would be another example of a valid argument. All right, so now we've seen several examples of what valid arguments look like when we're doing an Euler diagram. In the next lecture, we're going to go the other way, right? And we're going to take a look at some invalid arguments so you can see what to look for in those cases.